speaker is Sunggon Kim from SeoulTech. Sunggon, if you can hear us, please go ahead.
Sure. Hello, guys. It's morning Korea, so I'm fortunate that I cannot join you guys in the meeting. But today I'm going to talk about the exploring quantum simulation in HPC through memory and storage offloading. This is a work that I've been doing with my PhD student Sunggon Kim, and I'm not actually a quantum guy. I was never been. I started my research career with the SSD and operating system and how to build a system for a computing applications, not the quantum system. So this work is basically our journey from a HPC system perspective and how to optimize the quantum simulations in the perspective of the system architecture. So I will, in today's talk, I will talk about the traditional HPC science data management and how the quantum simulation in HPC can have some similarities or differences that we should tackle when expanding those simulations to millions or thousands of GPUs. Okay, so here we have a slide of the BPIC. I think people are really familiar with the BPIC, which is the state-of-the-art 3D electromagnetic plasma physics simulation. But I'm not really telling about the algorithm, but the thing is that these scientific applications are really becoming really big in terms of the number of particles, in terms of data size. They're really getting out of hands, and it's not just a story for the BPIC specifically, but there are a lot of usual suspects, you know, like QE, Quantum Espresso, AMREX, WRF, CSM. Those are the well-known scientific application that is growing exponentially, and they are getting out of hand in terms of both computation, but also in terms of the data as well. So in order to cater this kind of needs, what HPC does is to employ a parallel file system, which is essentially saying that rather than having single storage devices, rather than having few RAID type of storage devices within a single computer, let's have hundreds of storage servers or thousands of SSDs to cater those needs. And you probably heard the Lustre, which is the distributed file system used from Cori and now the Permuter. And people also, as they're employing those kind of distributed file system, they also design a various type of file management software, such as HDF5, which is the file format specifically designed to handle large-scale, exascale type of data. And as the storage goes, as the application produced a lot of data, what people did was to employ or design a new specific architectures for large scales of data. So you might heard or not the term called the burst buffer. People were raging about 10 years ago when they first built Cori, because they thought that it was a great idea to, rather than buy hundreds of devices for every different storage node, let's say, let's create a small subset of a storage node that is dedicated for very frequent data movement between the compute node and then traditional distributed file system. Also, as they develop this kind of software, they also develop, as they employ those kind of hardware, they also develop a softwares that provide a scalable query interface or data search performance like FastBit or Fast Query. But as there is, so these kind of the architecture changes were based on the premise that there is an I/O gap between the data, the speed gap or data capacity gap between the memory which resides on the CPU and then the parallel file system that was originally designed with the hard disk and then archiver storage, which is a tape storage. So people made this kind of shared bus buffer, or in recent days, what they do is that they buy a NVMe based or NVDIMM based, very expensive but very fast device for each node to cater the data to the computational device. And the reason we cannot just buy a really expensive device and then put it every elsewhere and then get maximum performance without hassle is that expensive devices are powerful, but they are also expensive because Premiere has thousands of storage devices, and it's nearly impossible to equip every one of them with a very expensive NVDIMM or NVMe, which is 5 times, 10 times more expensive than conventional SATA SSD that is stored on your laptop. And nowadays it's becoming more difficult because as the HBM, which is high bandwidth memory manufactured by Hynix, is almost going into the GPUs, there is more complexity from the computation device to the end tape storage, and managing all those layers is becoming really hard. So I have been collaborating with the scientific data management group in the Berkeley lab with Alex, Sim, John, Tong, and Strand, who is a professor now in OSU. And what we did was to analyze the application pattern, not just from the perspective of a single application, but rather from the perspective of the entire system. And that makes really tricky because when we look at 2-month-long logs or 3-month-long logs, we have 1 million, 3 million application executions with all different characteristics. And what application developers were saying is that their performance is really low. And when we analyze one by one, we just can easily say that, well, your program, the way you programmed is wrong, but you have to use this kind of specific library to efficiently handle the data. But when you expand that idea to millions of applications, then it's very hard for you to say that this is the problem and this is the problem that you need to fix, because that specific problem does not affect 99% of other applications. So is it beneficial to just fix that one problem for that specific user? And what is the cost of managing those bugs or updates every time? While we were analyzing those entire system data, we published HPDC and IPDP's paper last year. But the consistent theme that we got is that while analyzing the entire system can be difficult in terms of data, focusing on a single application and optimizing that application for new storage stack or new hardware can be doable for us. So while thinking about that, we thought about machine learning application, we thought about the climate application, but we quickly found out that emerging quantum simulation is one of the applications that experiences performance degradation due to the large amount of data. As you already know better than I do, that quantum simulation, when especially performing a full state simulation, creates a lot of data, really a lot of data, because it has to track every quantum state within the memory of the GPU. And if it overflows, it has to go to the memory of the CPU, and then it has to move to the storage and the tape storage and so on. And that creates a lot of problem. So we looked at a few papers, and the left figure was from the MIT, and then the right two figures were from the KISTI, which is the Korean government that runs the HPC, and they're building the in-house quantum simulation code. And what you see is that from the left figure, you see that the quantum computers, while while when you run the quantum circuits with the real computer, the performance stays relatively ideal. When you use the classical computer, it explodes exponentially. And more importantly, if you look at the left bottom figure, it shows the memory cost based on the increasing number of qubits. It means that as we increase the number of qubits, the data grows exponentially, and we cannot fit all the data to the HPC system. The Qista's HPC system has 0.76 petabytes of total memory within the entire node, but that can only scale up to 43, 44 qubits when we are trying to do the full state simulation. So as they develop the code, what they realize is that, well, we can use MPI, well, we can just spread the workloads to multiple nodes. We can improve the scalability with utilizing more computation devices. We eventually hit that roadblock where if the data cannot fit in memory, we cannot go on anymore. So after we find the problem, what we did was we looked at the quantum simulation benchmarks. So while there are many other benchmarks, we looked at the cuQuantum, which was developed by NVIDIA, and they have two different libraries to support the quantum simulation. The one was the cuStateBag, where it actually simulates the entire qubit space in the HPC system, and another one is the cuTensorNet, where it just does the amplitude sampling and then only simulate a few qubits, hence does not induce a lot of data overhead. And when you think about these large amount of data that quantum simulation produce and how much data there is available for the GPUs or the host memory, you can see that why that is becoming a problem, because GPUs are really expensive. I mean, really, really expensive, and we cannot really waste the GPU resources. But what people really forget is that while GPU can have a lot of power, it cannot really do anything unless you have the necessary data to go on. And while the classical HPC application were fine because they dealt with a relatively small data compared to quantum, they can fit their data into the distributed file system and then stage that data to the host memory and then GPU. Quantum simulation data, as I mentioned in the before slide, cannot even fit within the entire server's memory. So they are huge, and we cannot just rely on the existing storage system or existing data system to just store all the information somehow rather than optimizations. So here is the data that we run on the Permuter from the nurse, thanks to Neil. While we debugged it, the essential part was that it faces the OOM, the out of memory error, very quickly. So this was run with the cuQuantum, and then from qubits 1 to 48, it reached out of memory in the 48 qubits, and there is no specific way to solve that other than adding more memory. Sure, it can be considered as a problem of a single framework, but while we look at other papers, they only focused on the computation part, or they just assume that every data fits in that memory, but there is no efficient way or discussion on how to efficiently store the data to the storage. And we started considering about the performance disparity between the storage, DRAM, and then HBM within the GPU. So I'll our methodology was to simply slice the quantum circuits into multiple spaces and run them using multiple nodes and multiple GPUs. And while cuQuantum supports it, cuQuantum actually supports this kind of operation. The thing was that cuQuantum is black box, like many of NVIDIA software, and we don't know how they actually performed it. So we just thought that rather than relying on that simple functionality of the NVIDIA's code, let's do it ourselves with the traditional HPC application method, which proven to be effective. So we divided them into several memory parts and then copied the data using MPI and RDMA. And then we also used the NVLink, which was the data communication method in between the GPUs, and see what happens. So after just that simple method, we see that applying those kind of slicing can actually improve the performance very well. And especially it is effective when the traditional just bulk loading of the data was impossible. So in many cases, we were able to increase the number of qubits supported by the simulation by slicing the data. Well, yeah, this was expected because the slicing the data and distributing the data among nodes means that we're consuming more computation power. So we were expecting the performance improvement, but the important thing was that this was possible using the traditional distribution method that we already know from the HPC applications, and they were more effective than we thought. And the quantum simulation was indeed hurting itself for data management or data movement between the tape storage, discrete file system, and then the GPU device itself. And after we test those methods, what we're doing right now is to move that data stream to the no local storage, which is often called as NLS. So the NLS is you've already been using it, is just the high performance data storage that is directly located in the compute node. It is when we analyze the global system data, only 0 point something users actually utilize this node local storage. Despite that, this is the most expensive hardware and it's most powerful hardware that you have for the data storage. So it provides much faster performance, but the downside is that the user or the application developer has to consider this kind of performance gap in between, and then provide the efficient way to move the data from one source to another automatically, which makes it very difficult. So to do that, we are currently leveraging the cache or asynchronous components of the H265 cache flow connector, which is the aforementioned the file format for the existing HPC applications. The reason is that first, for the compatibility to H265, which is one of the widely used, and then the second thing is that people already done much of the hard work for us. We want to verify that if that can be extended to the quantum simulation, where the scale of data, the amount of data is much greater compared to the traditional HPC applications. So we are in the phase of moving from just the simple malloc and generation of data and then computation phase to actually using HDF5s to store data, read the data, and then communicate the data in between the nodes. So here is our continuing plan is to, when we get the quantum circuit, rather than just doing the malloc, what we do is that we first formulate the circuit and formulate the computation, and then rather than just continue with the computation or just exits the application if we do not have sufficient memory. What we do is that we first use HCF5 to store the data to the storage, and then utilize this kind of HCF5 library APIs to store the quantum information, and then reuse the quantum information from the distributed file system rather than going along with a single device and single memory. And the more detailed thing is that we will utilize the RDMA, which is the remote direct memory access that is widely used in the HPC applications, and they're highly optimized for this kind of not small, but the proprietary cluster such as Permuter, where it has a dedicated interface like InfiniBand, and then thousands of compute nodes. So we will distribute the data using RDMA to multiple nodes, and we also will use the MPI to store the data into the node local storage, and then continue with the computation with multiple nodes and then multiple GPUs. So for summary, what we aim to do is we aim to optimize the overall GPU efficiency or overall simulation efficiency by offloading data from the host memory to the storage. Based on our analysis, we know that this is ongoing problem for the entire HPC system, but this is more specific problem to the quantum simulation, where data size is extremely large, and we will optimize this parallel processing and data transfer, and also the scalability. So to conclude the all talk, we said that the HPC problems are data extensive, but the quantum simulations are extremely data extensive. And since the GPU is expensive, we have to cater that pricey device buying efficiently, giving the data to the computation device. And we are currently focusing on this kind of performance gap between the data hardware and the interfaces like HBM, DRAM, and then storage, and also the interfaces, which is InfiniBand, PCIe, CXL, and the Ethernet. And we are not just doing the simulation, we focus on the solutions for the existing hardware, such as buffer for node local storage. And the most important thing that we're focusing is the autonomous end-to-end data movement during quantum simulation without any requirements from the users, because previous experience and previous papers that I wrote found that users are essentially do not care about the hardwares, and they only care about their applications. So even if we build a great hardware or software, they do not use it. Yeah, so that's that thing, but it is true. So we have to overcome that. Okay, so that's the end of the talk. And if you have any questions, I'm happy to answer that.
I have a question. How do you slice the data, and how do you slice the gates? Don't you need to do an all-to-all almost after every operation?
So first, the NVIDIA actually has the API that considers the gate shape, and then does the slicing for us. So we first initially used the slicing technique to ensure the correct slicing of the problem. But after that, each slice is safe to slice again. So after that, we use just simple memory copy operations to slice the data into the nodes or the GPUs.
Do you have to do on all reduce at some point or anything like that?
I can hear you.
For operations, do you have to do any global operations at some point, or during running when you're simulating your circuit, or you're just storing data?
Yeah, so there are certain synchronization points that is applicable for entire nodes, but we are overcoming that because we since we are using HDF5, it means that we do not have to communicate to all nodes. We just have to communicate with the disparate file system that is globally available for entire nodes. So when the nodes need to synchronize the data, it will just simply use the file API to write the data. But other than that, it can just go on with its own parallel computations.
Do you have aging?
Aging?
Maybe
Oh.
one node is a bit faster than the other nodes, so they get out of sync. The state of the circuit.
Based on what we've been doing, there's no significant load balancing issue in between the nodes because the quantum simulations were so compute intensive. Based on our observation, the computation itself got great load balancing, but I don't know, because if we expand the number of qubits to extreme, and then if we complicate the quantum circuits, then it is possible that, as you mentioned, we might experience the load balancing issue and then need better ways to distribute the problem. Thank you.